Okay, here we go again. And we are talking about radiation, and very quickly, let's do a very quick review of my types of radiation. I can have alpha, right? And what is emitted from alpha? A helium nucleus. That means 2 protons and 2 neutrons are emitted. I can have a beta decay, beta radiation, and what is emitted? An electron. And then I can have positron. And in positron, I have a proton that becomes a neutron and a positron. And the positron is emitted, and its symbol is 0 plus 1 E. And then we have gamma. And in gamma, what is emitted? Energy. Only energy is emitted. No effect on atomic number or mass number. And we use something that looks like that as the symbol for gamma. Good. Okay, so that's our quick review, and let's get right back at it. Consider positron decay of C11. C11? Huh. I've heard of C14, I've heard of C12, C11. Hey, what do we call it when you have like carbon 11 and carbon 12 and carbon 14? Oh yeah, those are isotopes, right? Because they're all carbon, but they have different mass numbers because they have different number of neutrons. Okay, cool. Positron decay, that means it's got to be on the right side of my arrow. If it's positron, it's E0 plus 1. I start with carbon 11. Carbon is 6. So what's 11 plus 0? 11 equals 0 plus what? 11. 6 equals 1 plus what? Looks like 5. 11, 5. 5 must be boron. So this is my nuclear equation for the positron decay of carbon 11. Good. Let's see what you can do. There you go. Positron decay of xenon 118. Let's put me on pause and work this out, and then come back and let's get the answer. Well, you think you have this right? Positron decay. Okay, I draw my arrow. Decay, that means it's on the right side. Positron, 0 plus 1. I start with xenon 118. I look on the periodic table, and what is xenon? 54. Good. So 118 equals 0 plus what? Oh, 118. I got that. And 54 equals plus 1 plus what? Okay, I'm going to take this, subtract it from there, and I get 53. 53, when I look on the periodic table, 53 is, where's 53? Iodine. Good. So I have iodine 118. Good. So that is our positron. And finally, gamma decay of uranium-239. What happens in gamma decay? What is spit out? Let's take a look again. Where is it? Is it? Yes. Gamma decay. Energy is spit out, right? Energy is emitted. So I write my uranium-239. Uranium is 92. A gamma ray is emitted. That is energy. How does that affect my mass number? It doesn't. How does that affect my atomic number? It doesn't. That means I'm left with 239 uranium. I start with uranium, I end with uranium. What's the difference? Only that some energy has been released. I still have the same atomic number and the same mass number. Good. So that is really an example of all the types of radiation. I think we still have some more time today, so let's go on and consider something else. Let's move this down here. Boink. There we go. The neutron capture. Here's a new word, folks. Capture of nitrogen-14 and the alpha capture of nitrogen-14. Which of these is a nuclear transmutation? Okay. So we have a new word here, transmutation. What is transmutation? Transmutation. what is implied, what is meant by transmutation? Let's take a definition. Okay, this is a nuclear, I would say this is a nuclear reaction in which one nucleus is transformed into another. Now, what is required for me to have one nucleus transformed into another? That means what? The number of protons must change. Got it? Remember, my element is determined by the number of protons. If the number of protons changes, then I have a transmutation. So what are some examples of things that are going to make the number of neutrons change? Well, what kind of radiation? I can have alpha decay, right? Because I lose 2 protons and 2 neutrons. I can have beta decay because I have a neutron becoming a proton. I can have positron decay because in positron what happens? I have a proton that becomes a neutron, and then I can have some capture. Capture means that the particle is on the left side of my yields. So something like a neutron capture, well, let's not say neutron capture, let's say alpha capture. That means by something like uranium-238. Since it's capture, it's on the left side of my yield arrow. So I could have some types of capture. Now, not all capture, but what? Alpha capture, beta capture, right? Which is what? Beta capture is really what? Electron capture. I can have proton capture. All of these types of capture can result in a transmutation. So let us look at our question again. I have neutron capture of nitrogen-14. Here we go. I have a neutron, and it's captured by nitrogen-14. That means that's a 7. What do I get out of that? I get 15 and 7. 7, I look on the periodic table, is nitrogen. Did my nitrogen transmutate into something new? The answer is no, it did not transform, so this is not, no, this is not an example of nuclear transmutation. How about alpha capture? Well, my alpha particle is 4,2 helium plus 14, 7 nitrogen, goes to form what? 18 and 9. 9 on the periodic table is fluorine. Did my nitrogen become something new? The answer is yes, it did. So that is transmutation. Perfecto. Let's see. Okay, you guys give this one a try. Neutron capture of uranium-239, gamma decay of uranium-239, and beta decay of uranium-239, which is a nuclear transmutation. Put me on pause and come back when you have the answer. Okay, so let's see if you are correct. Neutron capture. I have 1, 0 in, plus uranium-239, uranium-239, 92. When I add those things together, I get 240 and 92. Is 92 still uranium? Yes. Did my uranium transfer into a new element? The answer is no, so this is not a transmutation. What about a gamma decay? Gamma decay. I start off with uranium-239. Decay means that my particle is on the right side. There's my gamma ray, and it does not change my mass number. It does not change my atomic number, so I end up with uranium-239. Start with uranium, I end with uranium. Is that a transmutation? No. No, no, no. And number 3 here, beta decay of uranium-239. I have 239, uranium-92. It's beta decay. That means my beta particle is going to be on the right side. I have 239, right? And what? I have 92 is equal to -1 plus something. Hey, I add a +1 to both sides, and I get what? 93. So 93, and I look on my periodic table, 93 is neptunium, Np. So my uranium went from being uranium to neptunium. Did a new element form? Yes, it did. That, folks, is a transmutation. Finally, let's see. Yeah, okay, finally. This will be our last one today. Electron capture of aluminum 26. Electron capture. Okay, how do I represent an electron? Well, an electron is really our beta particle. Its capture, that means it's going to be on the left side of my yield arrow. Aluminum 26. I look up aluminum on the periodic table. It's 13. And what do I get out of this? I get 26, and I get 13 and minus 1, or plus a negative 1. And what comes out of that? 12. 12 on the periodic table is magnesium. There we go. That is an electron capture by aluminum 26, giving me magnesium 26. All right. One further thing here. Let me go back to our overview. There's another way that we sometimes represent beta particles. Oh, that's transmutation. Let me go up here. Sorry. Another way that we sometimes represent beta particles are 0, -1 with a fancy B. In another way, we sometimes represent positron are 0 + 1 with a fancy B. So if you see these floating around sometimes, those are different ways of saying beta and positron. Okay, let us quit here. Next time we'll learn a little bit more about fission and fusion, and then do something on half-life, and then we are done. Have a good one.